So I don't normally do this, but I couldn't be here today. So, try and figure this stuff out on your own, but this is in case you need it. All right, the exponential model is below or the annual rate of increase. Find the monthly and quarterly increase. By the way, there's 12 months in a year, and there are 4 quarters per year. So that's kind of where we do all this stuff. So when you talk about the monthly, all you do is change the exponent to t over 12 because there's 12 months per year. And then you get to move, and I know some of you guys, you're just math is just really horrible, but t over 12 is 1/12 times t. Well, that's what it is. And we're going to throw this away for a little while. We're going to move the 1/12 to the interior, and we're going to see what that looks like. All right. And I guess I should have not paid attention to something in the first place here, but anyways. So we're going to take our 1.03. We're going to rooftop it to the 1/12th power, the 12th root, however you want to think about it. And that's a new number on the inside, 1.0025. Now, what I should have mentioned here was this 1.03, that lines up with 1 plus r. So the rate on the original thing was 3% per year. Well, now we have 1.0025, which lines up with 1 plus r. 1 plus r is from the exponential growth models, okay? And if we just take away the 1, we get that 0.0025 is r, but now that is per month. By the way, 0.03 is 3%. This would be 0.25%. And obviously, it's a little rounded. You want quarterly. Well, you just take your 1.03 and you raise it to the t over 4, and then you move that 1/4 to the interior, and you see what it looks like. So 1.03 rooftop to the 1/4 power is 1.0074. And remember, this piece right here is lining up with 1 plus r. So r is going to be on this 1.0074 per quarter. And I'm going to leave number 2 for y'all. It's the same exact stuff. All right, 3, in 2012, the population of a small town was 3,560. The population is decreasing at a rate of 1.7% per year. How can you write an exponential decay function to find the quarterly decay rate? All right, so let's start off with what's given. What's given is going to be a decay model. And we have an initial population of 3,560. We are decreasing at 1.7% per year, which is 0.017. And it's about yearly right now, right? So it's just a some time period in years. So we do a little math on the inside. We get 0.983 to the t. Now this is in years, but I want the quarterly decay rate. So since I want quarterly, I'm just going to introduce a /4. That's all I have to do is introduce that /4. And now I can feed this equation quarters. And I can move that 1/4 piece to the interior. and I will have a quarterly model. Now, the issue with these models is we end up doing a lot of rounding. These are rounded numbers. So 0.9957. But now the time is in quarters. And the quarterly decay rate, and again, which is what it's asking for. Think about your decay factor. Some of you know what this is, some of you don't because you don't take notes. So 1 minus R lines up. So 1 minus R is 0.9957. If we do the math on this by subtracting 1 and stuff, we have that R is 0.0043 per quarter, or 0.43% per quarter. Anyways, there's how you do it. Let's see, you are going to invest $1,000 into a money market account that pays 5.9% interest compounded continuously. So I saw the word continuously, which means that I used the amount after time is PERT. Which used to be a shampoo back in the day. Write a model describing your future growth of your account. So the amount after time is the principal of 1,000 times E, 5.9%, 0.059 to the 0.059 T. Easy peasy lemon squeezy, kids. What would the amount of your investment be in 10 years? Well, everywhere we see a T, we're just going to put T. So the amount in 10 years, that's how that's read. The amount in 10 years is 1,000 E to the 0.059 times a 10. And then I just go to a calculator and I push some magical buttons. And I get $1,803.99. It's not bad. It's really hard to make wealth. You gotta get lucky. When will your investment reach 15,000? Well, here's the setup. You'd say 15,000 equals 1,000 E to the 0.059 T. And we'll just stick that in Y1, and we'll stick this in Y2. Notice the E key is right there by LN. We'll do a zoom 6, although it'll be useless. Because you're going to have to play with your window on this, obviously. You put 15,000 into Y1, you're going to have to adjust Ymax. As soon as mine quits working, I'll go to window. I'm going to make the Ymax 16,000, just bigger than 15,000. And I know it's not going to happen in 10 years, but, you know, I'm going to hit graph. We're going to have to play with the window some more. We should start seeing the exponential function be drawn. And it's not moving too fast, is it? So back to window. Let's look 50 years in the future, X max to 50. It'll happen way before 50 years, because sooner or later it's going to trend upward at an increasing rate because you just have more money to play with. I thought it would happen a little sooner than that. But anyways, second trace, 5 for intersect, and you should be playing long, enter, enter, enter. 45.89 or 45.90 years. So time is about 45.90 years. Takes money to make money. But notice how quickly it was growing after that. All right, you decide to purchase a used truck for $16,000. The terms of this loan are 6.9% interest compounded monthly. So because of the wording of this one, they're telling us to use the formula for compound interest. The amount after time passes the principal times 1 plus R over N to the NT. for 5 years. All right, so compounded monthly tells me that n is 12. 5 years, t is 5. 6.9%, r is 0.069. We move the decimal 2 places to the left. And this guy is obviously my principal. So what we're going to do is we're going to figure out the amount you owe in 5 years. So t is 5, a sub 5, the amount in 5 years, is the principal of 16,000 times 1 plus r 0.069 over 12 months per year, raised to the nt. And that's what I'm going to push buttons on in the TIU4. 16, 1, 2, 3. 1 plus 0.069 over 12. And if I don't know what 12 times 5 is, if I don't know that 12 times 5 is 60, 12 times 5, just like that, or maybe the multiplier symbol, I don't know. But anyways, this is what you have to pay back. It's $22,569.53. And forgive me, I'm pretty tired, so my short-term memory is horrible right now. 53. This is what you owe. Okay? I want the monthly payment. 5 years is 60 months. So I'm going to take what I owe, 22,569.53. I'm just going to divide it by 60. That's how I get my monthly payment. I actually use a little bit different technique on this, but this is the gist of it. $376.16. That's what I can expect to pay per month. Life is expensive, kids. A certain rumor about you spreads around town at a rate of 300% every 4 hours. So 300%, if we shift that decimal 1, 2 places, is the number 3. It's 3. That's R. Only one person knows the rumor now. So one person would be my principal. It's 1. And I need a model. Okay. Notice that was every 4 hours, by the way. You're going to use the model for just plain old exponential growth. And in this case, it's going to be t over 4 because it happens every 4 hours. So the amount after time passes is the principal of 1, which is understood, times 1 plus 3 raised to t over 4. Now, obviously, you should figure out what 1 plus 3 is. So the amount after time passes is a 4 to the t over 4. I dropped the 1 because it's understood. 1 plus 3 is 4. But there is a model about a rumor. Rewrite the equation. Rewrite. Boy, that is really word up. Rewrite the equation so that it now represents how fast the rumor spreads every hour. So if we just move that /4 on the inside, we'll be all right. So the amount after time passes is going to be 4 to the 1/4 with a t on the outside. And I need to figure out what the 4th root of 4 is. I know it's the square root of the square root of 2. Ah, it was the square root of 2. 1.4142. Now to the t. Now, this is rounded, okay? That is rounded, so we're not going to use it. If there are 21,200 people in this town, how many hours until they all know? So we're going to set our population of our town equal to this guy. This is when your life is over, by the way. And we're going to y1 this side, and we're going to y2 that side. Now, obviously, we're going to play with the window some. We need to put probably 23,000. Well, how many people are in the town? We'll set the Y max at 22,000. And I don't know, let's look out 100 hours in the future, although I don't think it'll take that long. Let's look out 50 hours in the future. And once it starts growing, it starts growing. That's the thing about compound interest. Once it starts growing, it starts growing. So second trace, 5 for intersect, enter, enter, enter. So 28.7436 hours. 28.7436 hours. And your life is over. All right, that's the rumor question. I think up next is a cockroach. A residual pesticide kills 26% of all pests every 17 hours. Now we are killing, so this is decay. The amount after time passes is the principal times 1 minus r to the t. And here it's every 17, so over 17. My rate of decay is 0.26. And I have a principal. There's 1,000,000 cockroaches. Sounds kind of bad. But my model would look like this. The principal of 1,000,000 times 1 minus r. So I'm thinking 1 minus 0.26, which is 0.74. 0.74 because there's 74% left every 17 hours, sitting over t over 17. After 4 days, how many cockroaches remain? A day is 24 hours, so I've got to figure out what 4 times 24 is, and that is 96. And so I'm actually doing, the reason I'm doing hours is because this is hours, right? That's 17 hours. So a sub 96 hours is 1,000,000 times 0.74 to the 96 over 17. And we'll just push buttons and we'll see how many cockroaches we have left. Maybe. All right, sorry that took so long. I didn't sleep much last night. But that's just an excuse, right? We're down to roughly 183,000. There's 182,619 because we round life forms up. 182,619. All right, when will there only be one cockroach? I want that to the day, hour, minute, and second. So we're going to set 1 equal to our equation. We're going to put that in y1. We're going to put that in y2. Yeah, it's 1,000,000. I'm struggling today, aren't I? Let's see, and this was x over 17. I'm going to zoom 6. And you'll see the y equals 1 line. We're going to have to look pretty far in the future. I mean, 96 hours got us down to 182,000. So let's go out 500 hours and see what happens. I suspect we'll at least start seeing the graph at 500 hours. I could be wrong. I probably am. I thought that would happen. All right, let's go out 1,000 hours. There it is. So second trace 5, enter, enter, enter. 780.00567 hours. 780.0. I wish things would work like they're supposed to here. 0567. Okay, so I want this to the day, the minute, hour, minute, and second. So I'm going to have to do some math. I'm going to divide this by 24 to get to days, okay? I want to go into days first. That should make sense to you guys. You guys should know basic time measurements. But I know that you don't. And you will breed like crazy. 32 point blah blah days. That's 32 whole days, right? 32 days. Now, I'm going to take away the 32 days. It's 32 days, and then you got this decimal. There's this 0.5002365. 00 dot 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 days. Well, I'm going to take that and I'm going to multiply it by 24 to take it back into hours. And I'm going to get 12 hours and a little bit left. Now I've got this stuff left over here, this 0.00567. And that's still in hours. So I'm going to multiply it by 60 to get to minutes. Maybe. Let me take away the 12. Multiply that by 60, and I'm going to get into minutes. 0.3402 minutes. I'm not going to write that down. I'm going to multiply that by 60 again to get to seconds. 20.4 seconds. All right, according to your mathematical model, can there ever really be no cockroaches? And the answer to that is no, because this thing is decreasing and it's going to have a horizontal asymptote of y equals 0. If you're only getting rid of 26% of something, it's never going to disappear. It will disappear into what we call essentially 0, but there's always a piece of a cockroach left. So according to a mathematical model, no. And I would argue that even in the real world, you can't get rid of cockroaches. Cockroaches and glitter will be the last things that inherit this earth. Typical student's attention span decreases roughly 15% for every 6 months in class. You are probably well past that point. Write a model describing a typical student's attention span. So after some time passes, we have their initial, by the way, the initial attention span is 100%. Okay, and we'll just use that number there. It's 100. Here we have 1 minus 0.15. And this would be per 6 minutes, okay? T over 6 minutes. When will the student's attention span be 70% of what they started with? And it's not 12 minutes. This is 70 equals 100. This is going to clean up to be 0.85, and we'd have T over 6 as an exponent. And we'll use a TI-84 for that. Okay, everybody sees me clicking that, right? Go to Y equals. Put a 70 in Y1, put the equation in Y2, 100.85 with an exponent of T over 6, and then do a zoom 6. Of course, the x-axis is only out 10 minutes here. A typical class time is 48 minutes. So let's just set the X max to be 50. And we put what, a 70 in Y1? So change the Y max to be 80. We'll start seeing some stuff. All right, let's hit second trace, 5 for intersect. Enter, enter, enter. So it takes 13.168 minutes for you to have 70% of your initial attention span. 13.168 minutes. And I've only got 70% of your attention span. And this video has already been over 13 minutes. So, you know, we're in trouble. How much of your attention do I have after 48 minutes of class? The truth is 0. 0%. But according to the mathematical model, I would say the amount in 48 is 100 times 0.85 to the 48 over 6. Now we could simplify 48 over 6 if we wanted to, because I know it reduces. It's 8, isn't it? But let's just push buttons and let's assume you don't know what 48 over 6 is, because God bless you, you don't. I have 27.25% of your attention span. And that is very optimistic. Anyways, there is all the stuff in class. Next thing you'll be doing is taking a quiz. Good luck on it.